Hi everyone, welcome to this talk about GstWebRTC and WebKit. So my name is Philippe Normand. I'm here with my colleague Carlos Benzem, and we both work for Igalia. So let's see what's the outline of the talk. After a first introduction, like really brief introduction, we'll talk about the changes we made on the pipeline in WebKit regarding WebRTC between the last stable release, which was 242, and the new one, which is 246. We'll talk about what's new in the backend. Then we will have some some videos about the practical use cases we've been focusing on the last year. And then we'll talk about the ongoing work, the task we are working on currently, and then the plans for the future. So what is WebKit? I guess many of you know it already, but just a quick reminder. It's a web engine maintained by Apple, Igalia, and Sony. And it allows you to build native applications like browsers, newsreaders, whatever you want to embed the web into your desktop or embedded product. And it's split in various ports, which are platform specific. Apple maintains its own ports for their hardware. And then Sony also has a port for their PlayStation device. And on Linux, we have two ports, one for desktop and one for embedded, which is called WPE. So WebRTC, quick reminders again, very brief. It's about real-time communication on the web. You have the basic use case that most of you know already is a basic chat application, but you can also have more use cases such as cloud gaming, online auctions, anything that require low latency, basically. You can do broadcasting and also native applications with like WebRTC source and WebRTC sync. So in WebKit, WebRTC is split in various specifications. First, you need to access some device, like capture device, and that can be done with get user media. And on the backend side, we use Pipewire or Video for Linux, depending on what's available on the device. Then if you want to do screen capture, you have to use get display media, also using Pipewire on the desktop. On embedded, I don't think we do that on embedded. And then if you need to play those streams, basically you can create a video element or an audio element and connect that media stream to the video, or even more things such as Canvas, WebGL, or WebAudio, whatever you want. And then for the peer-to-peer connection handling, there's an interface called peer connection in JavaScript, and that's backed by WebRTC bin on the backend side. And the current status is that those features work, at least the first ones, work very well. They are well tested on the development boats, but we are not enabling them in releases yet. So they are like considered experimental features so far. So we have two backends currently in WebKit regarding WebRTC. One is based on only WebRTC, where we have some basic infrastructure for using GStreamer decoders. And it's used by some people, but it's not shipped in releases for various reasons. One of them is licensing for GPL applications. It's not really compatible. And the second backend is GstWebRTC, which is what we are about to talk about here. And we use WebRTC bin and the lib GstWebRTC library. Hopefully, the goal is to ship that in stable releases at some point in the future.
Yeah, and so since we're here in a GStreamer conference, we have to show pipeline changes, right? Since we already presented last year what was the status of WebRTC in WebKit, we're going to present the changes in the pipeline between what we presented last year and what we have now. And just as a brief recap, when we're talking about WebRTC in WebKit, usually you can have from 1 to 3 pipelines involved, right? So the WebRTC pipeline, which is the one we focus here, is where WebRTC bin will live. That's what's handling the network side of things. But when you have capture elements, or in that case, you're using media stream to capture your webcam, that's going to involve some Pipewire source, some Video for Linux source. That's the capture pipeline. And the playback pipeline is where playbin lives. So that's the code for the video element. And this code is shared with other applications of the video element, like MSE and other applications. And let's take a brief look into what we had last year. We split the presentation into the receiving and the sender side because the pipelines get pretty big, so it's not so useful to show all of that at once in a slide. And in the receiving side, what we had in 242 is that there were a few elements that we used to use, which is the valve element, for example, for muted and inactive tracks. And we also had this weird thing with the T there, and the end of the WebRTC pipeline would go into app syncs, and that will be handled to go into the playback pipeline later. But for testing reasons, we had some dynamic pipeline changes there with a fake video sync. That's mainly for getting stats in tests and in some cases, but it also created other issues. And what we have nowadays is a simpler pipeline, so we don't need the valve element there anymore. Now, after WebRTC bean creates those source pads, they're connected to a bean that has parse bean, and that will basically go into fake syncs, and we will use the handoff signal to capture the buffers and signal that to the WebKit observers. So that will forward the buffers to the next part of the WebKit pipeline. Let's say going into the playback pipeline. On the sender side, it's you can see that it's not a comparison between last year and now because not much has changed. The sender pipeline basically will connect to a MIDI stream source that is generating buffers from the capture pipeline, and then it will have the WebKit encoder, which is a bean that has encoder and configurations there, a payloader, and then it goes into WebRTC bean. One tidbit is that the WebKit encoder element there is also reused for web codecs, for example. It's the same class that we have in WebKit, and we're reusing that in WebRTC. What we have now that's new is support for AV1 encoders. That's also a topic that was brought up in the conference here, that there's no standard API for setting properties in the encoders, like bit rates and things like that. So adding new encoders, we had to add those encoders specifically there to support the properties listed there. And another change that we have is regarding the replace track API. So as the name suggests, it's an API used basically for having a peer connection and replacing an old track with a new one. And it used to be troublesome in the past with that because the old implementation was basically creating a new MIDI stream source, unlinking the previous one, and then relinking the new one. And doing this unlinking and relinking caused also issues in some situations. And nowadays, we reuse the same MIDI stream source, and we basically just stop observing the buffers from the old track. And because we are just reusing the MIDI stream source and pushing those new buffers in the app source, also the caps handling is better handled there. We don't have any more issues with that. And what's new? So there are also some new APIs or fixes that we did recently, and one of them is track events. It's an issue that is kind of easy to show because during negotiation, basically, you're going to have your signaling there, and there's one specific situation which is when you're applying a remote description from a remote offer. We saw many applications were depending on the timing for the track events to be emitted. So you can see here on this on-track event, basically this assertion was failing because in the WebRTC bean backend, this track event was emitted way too late, only after things were connected in a stable signaling state. And although it was easy to have a test for that, fixing that was a bit tricky and had to go all the way to WebRTC bean and implementing some changes for creating the transceivers early during the negotiations to be more spec compliant. And hopefully this will be released in the 126 of GStreamer.
Yeah, another thing is legacy offer options. In the peer connection, there was those Boolean flags you could specify when you're creating your offer, specifying that you could you would like to receive audio or video. Nowadays, it's better to use the transceiver API in JavaScript, but still, these options are still available in Chrome, and so many websites still use those. So we decided to bring those back because we needed it for an application we'll show later. And it's gated behind a runtime flag, and it's disabled by default. And internally, what we do is basically what you would do in JavaScript, like creating a transceiver that would be receive only, depending on the media type you want to receive. And it's transparent to the application. Another thing we worked on a bit is RTP2 payloaders. As you may know, the payloaders from Good have been kind of rewritten in Rust. And the nice thing about that is that they have the same public surface API, like properties and signals. So you can they can act as a swap-in replacement to the RTP, like the old C versions. So what we do in WebKit, we rely on the rank of the payloader to do the selection at runtime. So if you have the Rust payloader with higher rank than the C version, it will be used. And it's transparent for us. And for incoming streams, Parsbean is actually doing the selection for us, so we don't really need to do anything on that side.
Yeah, now we can get to some practical use cases just connecting to what we presented before. There are some applications that we've been testing and also making that work. One is Amazon Luna. It's a cloud gaming platform. It was already demoed last year in the GStreamer Conference. And this year we basically kept up with also the web app changes. So they were changing things in Luna that broke our backend. Then we also fixed them and make sure that it continues to work. And yeah, it's a typical cloud gaming setup. So you have a game that is rendered server side, and you can play that in WebKit, and that should be supported nowadays. Basically in WebKit side, it's using a receiver only, peer connection, and with our backend we can do hardware acceleration, decoding, and all the stuff that you get with GStreamer. Another one is a CAD application. So this is an application that also does rendering server side, and it's doing for industrial modeling. So this is a WebRTC stream that you're showing here, and basically you can write your model as a piece of code, and then you're going to render that in the browser with WebRTC. To get that working, we had to fix various things, including what I mentioned before about the track events. They were relying on that behavior from the spec. We also had to fix some things with interacting with their SFU, because they were not sending keyframes at the start, and that caused some issues. We also fixed that. And after many small fixes, now the application is running smoothly on WebKit GTK.
Yeah, so let's talk about what we are working on right now, or the features we are working on. First one is simulcast. That's been available for some time in WebRTC bin already, so we're trying to use it in WebKit. What this is about is like if you can configure your transceiver to send multiple versions of the same video stream, and that can be used by an SFU, for instance, to adapt to the networking conditions or to select a different version to send to the other participants of the video room. So when you create a transceiver, you specify a RTP stream ID, maximum bitrate, and then if you want to scale down the video resolution, you can also do it with that scale resolution done by. So on the sender side, so we basically split the video stream and encode it multiple times, basically, until we could use more advanced things like SVC, for instance. So yeah, we encode multiple times, we payload multiple times, and then we feed that each RTP stream to a funnel, and that goes to WebRTC bin. So yeah, that's it. And then on the receiver side, WebRTC bin will create a source pad for each stream with different SSRC, sorry. And it's transparent for us as well. So we use the existing infrastructure for incoming sources for that. Yeah, but still we have some challenges to solve. On the sender side, we have a MID RTP header extension to use. And if you enable FEC in WebRTC bin, the encoder will like try to protect the buffers and then remove that that information from the new buffers. So that's an open issue currently in GitLab. Need to find a way to work around that so the MID is kept even if FEC is enabled. And on the receiver side, we also would like to have the MID available. It's not the case currently. We have a patch work in progress for that, but we have to like plumb a new signal from PTDMux, which is where the caps are set for incoming streams, to RTP bin and WebRTC bin, where the MID information is available in the SDP. So yeah, we have to make a synonym across 3 different layers of the stack. So, yeah, and hopefully we plan to ship that. We probably will need to get it properly at runtime. Yeah. Another thing is SFrame, which is end-to-end encryption. You might wonder why that is needed, because there's already some protection like with SRTP in WebRTC. But this is about end-to-end encryption. So if you want to interact with an SFU and keep the encryption working, you need another layer of encryption. So that's the purpose of SFrame. And it's combined with encoded transforms in WebKit. And you have a small example there in JavaScript where you import a crypto key and create a transform element and then associate that to the sender associated with the video track, for instance. And then on the receiver side, it's the same, but you do it when you receive a track event, basically, on the receiver. So the workflow, that's a schema from the RFC I stole from the. I thought it was nice. So you have the workflow there. You have 2 options actually with SFrame. You can do the encryption before packetizing or after. But actually, most browsers, and it's mandated by encoded transform, you have to do it before packetizing. And then you have the op-by-op protect, which is usually like SRTP. So on the RTP packet, you will have the payload would be a SFrame header, and then the encrypted part in the payload section, and then that is wrapped into the SRTP authenticated portions. So yeah, you might wonder how to packetize that with GStreamer. We need a new kind of generic packetizer for that, I think, because the existing video payloaders, for instance, expect metadata, for instance, in order to know how to split the frame in multiple packets, for instance. And so yeah, it's tricky. But so far, we still made some progress. At least we got the generic crypto support working with OpenSSL, and that is covered by layout tests in WebKit. And then we need to integrate that into the backend that is used by WebRTC. They have like a callback system there for encryption and decryption. We need to integrate that somehow into our backend. And yeah, there's also callbacks for metadata handling that needs to be used. So yeah, very much work in progress, but eventually we'll get there. Another thing we're working on is DevTools, because as you might know, perhaps in Chrome you have WebRTC internals. We would like to have the same kind of thing in WebKit in order to do live inspection of the pipeline and even post-mortem analysis if needed. So to check the logs and so on. And we wanted to have it supported for libWebRTC and GstWebRTC. So we came up with a JSON stream format that is emitted by the backend. And it can be then used later on for graphing purposes or post-mortem analysis. And you can see there an example of a really basic frontend I've built, where you can see the bitrate information, frame rate, and the QP graphs. And the graphs are actually, we use the same canvas-based graphing library from Chrome. So it's the same kind of thing. It's not very beautiful, but at least it works. So yeah, we have the backend working. We have a pull request submitted. We need to iterate a bit on that because Apple people also have logging facilities. So we need to make that work some better with their infrastructure, because eventually they would like to use that as well. And then on the front end, we have few options. So we have a full standalone web page that I just showed on the previous slide. And we could use that, integrate that page into WebKit as well using a custom protocol handler, or even with the web inspector. We're still up in the air to which approach will be used exactly. And we hopefully plan to ship that in March into 48. Also, we have plans regarding sandboxing. I talked about that last year already, but the plan remains. We still want to use the camera portal for sandboxing of the capture devices on desktop. On embedded, it's going to be tricky to use the portal, but that's the way it is. So on embedded devices, we still need to allow list video for Linux devices in the sandbox. Yeah. So this is a bit of a spoiler for a presentation this afternoon about LibRise. So yeah, currently in WebKit, the RTP, all the network is done in the web process, and that's a sandbox violation. So if you want to do WebRTC right now in WebKit, you have to disable the web process sandbox, which is really bad for security purposes, obviously. So we want to fix that and move all that networking into the network process. How we will do that? So there's an abstraction in WebRTC now, in GstWebRTC, so that you can build your own ICE agent. And we will have one eventually in that will rely on LibRise, which is an alternative to libnice developed by Centricular Folks, Matthew. And it's written in Rust and using the Sans.io design pattern. And we really like to use that because it's a really clean design and it fits really well in our infrastructure, I think. So the plan is to use that next year eventually and to work with the LibRise maintainers and also help them to close the feature gaps in LibRise and iterate on that, yeah. So yeah, that's it, I think. Thank you.
Questions? I guess not, then thank you again.